Hi, and welcome to day 3 of the C++ Bootcamp. We have a lot of material for you today. The first item is an introduction to C++ 11, followed by a discussion between Patrick Scheller of the Google C++ group, a developer and project manager, and Bruno Babet, one of our compiler engineers. That interview will be interesting to people who already know C++, and who follow various compilers who are interested in the history of compiler development, compiler extensions, that kind of thing. First up, though, is the Bootcamp event of an introduction to C++ 11. In Monday's session, we ran a quick poll of attendees and found that about 80% of people who replied are still using an older version of C++. We've also had a number of questions from people completely new to C++. So this topic is going to show a snippet of C++ 98 code, i.e. code written in an old style. It's not bad code, but it's not great. I'm going to very quickly run through this and explain what each piece does for those completely new to C++. It covers containers, standard algorithms, streams, loops and iterators, and classes and structs. But then I'm going to examine this with an eye to updating it and go through the code and edit it live to make it a bit more up to date. Since it's artificial example code, it won't end up perfect, but it will show some of the new C++ concepts, and importantly, explain why I've made those changes. Because this is a lot of material, there's a lot to cover, but that's what a bootcamp is all about. We will go through things fast, but the replay will be available, and at the end I will link to a number of resources to find out more and to learn at your own pace. So let's begin. Remember, after this we will have a Q&A, and then we'll go straight into the more technical conversation about compiler history and extensions with Patrick and Bruno. I have here roughly a page of code. This is a command line or console application. I'll show the bits above this later, but let's look at the code on screen. For those completely new to C++, I'm going to give a quick overview of what it does first. I'm not going to explain what a class or object or a pointer are, but we can answer that in the questions or point you at resources if you need. If you already use C++, stick with us. We'll get onto the C++ 11 items soon. This is going to go very fast. If you have a C++ Builder starter, don't bother about following along at home. We'll put the replay up and you can download the code and have a look in your own time. And just a reminder, this is old style C++. It is not very good code. We'll fix all the problems very soon. The top 7 lines are 2 example containers. At the top is a vector called items. A vector is like a dynamic array, that is, it is an array or list of items, and the number of items in the list can be expanded or shrunk. The angle brackets indicate this is a template, that is, a vector of ints. The items it contains are ints, or numbers. A template is a generic thing, where you fill in the generic spots with something specific at compile time. So the vector has been written to hold any kind of item, and we're telling the compiler to replace the unknown generic type with a specific one, int, so we get a vector of ints. You could get a vector of strings or a vector of apples, anything, just as long as you specify a real type to use. The stud : at the beginning indicates it's in the standard namespace, something that doesn't really matter at the moment. We go on to add 3 numbers, 3 ints, to the items vector. Below it is a map. A map is a fantastic data structure often called an associative array, which is a way of saying it stores a bunch of key-value pairs. For any key, you can look up and see if the value exists and what it is. It's like an index. You could associate a person with an ID code, for example, and the key is the ID code and the value is the person. Then when you give the map the ID code, it gives you the person for that ID code. Here I'm adding a key of 1, that's the ID, with the value of a string or text, 1, ONE, and so forth for 2 and 3. Below that is an example of using I/O streams. I/O streams can be used to read and write to the console, to file, etc. Here we're writing out to the console. WC out means wide character out, and we're using the wide version because that accepts Unicode. Often, if you're learning C++, you'll see just C out or C in. The double arrows are an example of an overloaded operator. An operator is something like add or multiply, The double angle bracket is usually a bitwise math operation, but has been overloaded, that is, given a custom definition, so that they write the items they've been given to the stream. It's too much to get into now and is arguably a good example of confusing code, so we're using it just because it's common. Here we are printing to the console the values for various keys in the map. If I give it the number 2, we should print out the string 2, because that's what we associated with the number 2. If we give it 5, there's nothing there. We will print out nothing. Now we get to something much more interesting. The standard library, which is something you'll use a lot in C++, has much more than containers. Among other things, it has a family of algorithms, that is, standard algorithms you can apply to a range of items. That can be to sort items, to find items, etc. Well, here we're just going to do something to every item. That is, for each item, we are going to do something. I'll come back in a moment to what that is. Next, we have a loop, which loops over all items in the vector and prints them out. Both these use iterators. An iterator is something that points to or refers to an item in a range of items, and can be moved to refer to the next or previous one. A vector or map are just collections, and so you can have a loop that starts at the beginning or first item, is incremented to refer to the next item until it gets to the end. An iterator has pointer semantics, so you can dereference it to see what it refers to. If you're interested, you can do that by operator overloading again. Operators star and arrow can be overloaded by any class. We're not going to cover what a pointer is today, but in C++, the star lets you dereference a pointer to access what it's pointing to. The arrow operator dereferences and lets you access that item's fields or methods. Here the iterator is pretending to be a pointer because an iterator, as something that refers to something else, is similar in concept to a pointer. Don't forget, we can give you many references to learn about this later. Finally, we have an example of a dynamically created object, that is, an object created on the heap. Here one is created using new, which allocates memory in the heap, which is what you normally think of as computer memory, and makes an instance there. It calls a method on the object, and then gets rid of it. It's important to always delete what you knew, otherwise you end up with lots of memory that's used even when you're done with it, and that's called a memory leak. The heap is opposed to the stack, which is automatically allocated and freed. In C++, you can create objects on both the heap and the stack. The two variables items and map are created on the stack. Foo is on the heap, and you can see that because it is created using new and we refer to it by a pointer. That's all going very fast, but is a very quick introduction to C++ and some basic concepts. Containers, templated types, iterators for looping, algorithms, and creating and deleting. We'll make this code available and you can run it and see what it does, and running the code and stepping through it is a good way to see how it works. To do that, place a breakpoint anywhere in the code, and click this button to run with debugging. It will run until it hits the breakpoint. You can then step, that is, run line by line, or click run again, which will make it run without stopping until it hits this breakpoint that I placed at the end. You can switch over to the console to see its output. Now onto the C++11 part. This code is not modern C++, and I'm going to point out a few items that are not. We initialize the vector and map by manually adding elements. We use a functor for our algorithm. We loop using begin-end. And we manually control the lifetime of foo by manually deleting it. I haven't dwelt on the functor struct since we're going to get rid of it, but it is a small class or struct that has an operator bracket, allowing it to be used as a function object. So let's go through and change it. The first step is to make sure we're using the new Clang compiler. Go into the project options and in the compiler settings make sure Use Classic Boolean Compiler is not checked. Before really getting into C++11, a bit of code maintenance, again for those new to C++. Let's move the foo class to its own unit. This is an organization and style thing but makes the code neater. You can add a unit by right-clicking on the project and selecting Add New Unit. C++ often splits things into two files, and you put the declaration of the class into the header, which is included into other files that lets the other files know about whatever's in the header, such as this class declaration. Here's the declaration of foo. Let's make sure it's just the declaration, that is, just saying what exists. There are no method bodies in the header. And it's implemented in the CPP file. The colons here indicate scope, so the constructor or do something method of the foo class. The same syntax is used for namespaces, which we won't get into today, but std : is a namespace. Back to the main code. Look at all this code manually adding items to the vector and map. Wouldn't it be nice to be able to declare and initialize the container in a single statement? Yes, it would. And one of the smaller features in C++11 is new initialization syntax, which we're going to take advantage of here. To the end of the vector items declaration, add the elements inside curly braces, like so. Now you can delete the manual addition of items. Neat, isn't it? This is uniform initialization syntax. In old C++, there were several different syntaxes for initializing things. Let's do this for the map too. A map takes 2 items at a time though, so how do we declare those? It's actually quite simple. You declare each pair, where each pair is also initialized using the same uniform initialization syntax. I'm going to put those on different lines so it reads more clearly. Already we've written less code more clearly, and as a side effect it will actually perform better too. One of the big new items in C++11 is Lambda functions. There seems to be a bit of mystique about them, perhaps because of the name. They're actually quite simple. And let me take a moment out to talk about them. Lambdas are anonymous functions, i.e. just methods without a name, and can be written inline instead of externally somewhere else. That's all. It's really much simpler than you might think. The one extra really useful thing is that they can bind to or capture other variables by value or reference, to make those variables accessible inside the function body. They also behave like objects, so you can assign them to a variable. They have 3 parts. The variable or capture list, square brackets, this is the only unusual part. The argument list, in round brackets, just like a normal function. The code, in curly brackets, just like a normal function. For example, this lambda, where you have int n equals 5, the lambda in square brackets, n reference, in round brackets, int I, and in curly brackets, return I plus n, binds to n, which is a variable outside the lambda, by reference, and when called has a single int parameter and returns the sum of the 2 ints. For what it's worth, that makes the simplest lambda this amazing bit of code, bracket bracket, bracket bracket, bracket bracket, which is a lambda that captures nothing, is past nothing, and does nothing. So let's go back to the code. We can write a lambda that captures the map by reference since we don't want to copy it, and then does exactly the same thing as the functor except inline here in code. The neat thing about this is that you can see what your code is doing. If functor is external, what it does is declared somewhere else, so you can't necessarily see it. A lambda you can see, so you can read your code and see what operations you are applying right there. By the way, as well as being inline in code, lambdas are inlineable and optimizable, so you lose absolutely nothing in performance compared to a functor. Let's delete the functor now. Deleting code is always a good thing. This lambda is run on each item in the range begin to end of items, which is a very simple algorithm. It is effectively a loop, and so for each item uses it as a key into the map and prints the value for that key. Next, let's talk about type inference, or the auto keyword. I want to suggest upfront that you don't use this keyword everywhere, but in many places it can be very useful. Auto lets you not write what the type of a variable is, but lets the compiler deduce it for you. This is useful, for example, with lambdas. A lambda is an object, it is a function object, and so if you want to assign a lambda to a variable, why try to figure out its type, even if you can? You don't care, just let the compiler figure it out. But let's look at another use case, iterators. Suppose I change items to be a list instead of vector. List is another container. All of a sudden, the loop here won't compile because it specifies a vector iterator, not a list iterator. So let's say we don't care, it's something the compiler can figure out for us. We use auto. Now we can change the type of the container and not have to update our code. This is important because updating the type of the iterator is not a meaningful change. It adds nothing to our code. It's just bookkeeping that makes life difficult. Not having to do it makes refactoring and changing types, like changing the underlying container, much easier. This is a goal of C++. Back in the days when the STL was being written, the algorithms were designed to work regardless of the container they were operating on. Notice that we never got a compile error at the for each when we changed the type of items. It works on both a vector and a list. It was templated. The interface of using begin and iterators was the same, even if the types of the iterators were different. Being able to do something like change a type but keep the algorithm is a design goal. Auto, in this situation, lets us achieve something similar in normal non-templated code. The compiler deduces the type and uses that for the variable. So it's great for code like this. Auto is very useful in templates too, for example for intermediate variables in a templated function. However, don't overuse it. If you write auto I equals 5, you're not really gaining anything. It's useful for where types can change, or where types are lengthy or complicated, or where you don't actually know what type you'll have. But we're not done. C++11 has what's called a range-based for loop, where a range is something like all elements in a container. Here's the equivalent of the loop with all the iterators. Auto I : items. It's neat, isn't it? You can have a method return a range too. This example is simple since it goes over all elements in items. But you could use this to go over the range of a filtered subset of items too. Finally, I want to discuss the lifetime of objects. Stack-based objects have a lifetime controlled by their scope, such as the block they are declared in. But dynamically created objects have to be manually deleted. Now, even in old C++, you're probably already using smart pointers via the boost library perhaps, but if you're not, a smart pointer is an object that looks after another object's lifetime. You give it a pointer and at some point, depending on what kind of smart pointer you're using, such as when the smart pointer goes out of scope or the last reference to the pointer it holds decrements to 0, the smart pointer's pointer, like the pointer that the smart pointer holds, is deleted. In C++11 there are two types of smart pointer, unique pointer and shared pointer. Shared pointer might be familiar to you from Boost. Let's go ahead and make this a unique pointer. We can delete the delete line because foo will be deleted when the unique pointer goes out of scope. For example, if I put extra braces around it to create an extra block, it will go out of scope here at this close brace, and that's when foo will be deleted. Let's look at the declaration of test too. It takes a pointer. Well, we know right now that foo exists because we have the code in front of us, so it's better to change it to a reference. And because a smart pointer has pointer semantics, you can dereference it in the call to test. Now, here are two possible mistakes. First, because you have a unique pointer object, you might want to pass that to the test method. If you do that by value, you change ownership of the pointer and you will not get the result you want. If you do it by reference, sure, it will work, but why? The smart pointer is used for ownership, and passing one around is confusing, indicating that you might want to change ownership. Here, just pass a reference to the foo instance instead, and leave the unique pointer at the base level. It's much clearer and cleaner. The second mistake you might make is to use shared pointer instead of unique pointer. Now, shared pointer is really useful when many places might refer to the same pointer and you only want the pointer to be deleted when the last reference vanishes. It keeps a reference count for the pointer. It's very easy to use, whereas with unique pointer, ownership changes, which can be confusing until you understand it. I won't get into the details here, but I'll add some resources at the end. However, it is less performant because it needs to keep that reference count in some external place, and does so in a thread-safe manner too, that is, with an atomic increment and decrement. It's also perhaps confusing. Using a shared pointer clearly indicates the pointer is supposed to be shared. Here, the pointer clearly is not. There is no other object also using it. I've seen a lot of code using shared pointers where doing so obscures the ownership of the pointer, where the lifetime can be controlled in a much more fine-grained manner. Try not to do that, it's unclear and slower. And similarly to passing a unique pointer as a method parameter, passing a shared pointer can be a code smell. You should do that when you need to, because it indicates something in the method will also take a reference to the pointer. But often a method can just take a pointer or a reference instead of the smart pointer object. In the end, that makes the ownership semantics much, much clearer. So let's look at what we have. I've removed the stream code because I don't personally like streams very much, and because I included them only so you can see the behavior of the code when you run it at home. For example, you can see when foo is created and deleted, and experiment with different types of smart pointers or with not using one at all. So here's the before code on the left and the after code on the right. You can see the C++ 11ified code, which is still not perfect but is better, is smaller, cleaner, has less code, has clearer code, looks after its object lifetimes reliably, and will be faster and easier for the compiler to optimize as well. That's good stuff. So that's a C++ language deep dive. A quick introduction to the language, and then some typical old-style C++, and then some of the major C++ 11 features and the benefits they bring. Let's move on to a Q&A, and then after this we'll show a great technical conversation between Patrick Scheller of the C++ Google Plus group and Bruno Babet, one of our compiler engineers. Stick around for that if you're interested in history, compilers, and so forth.